I know. Thanks. Where do you start with this? I taught you to ask a question every time you see this reagent in a reaction anyways. You guys remember what question I taught you to ask? I mean, I don't think that I really laid into it saying this is the question I want you to ask. But I had you ask a question. I can set you up with the premise. If HCl is the acid, if HCl is an acid, what's the question? What is the base? Exactly. What is the base? And that's actually one thing I want you to recognize. You guys might feel like you look at this and say, I don't know what I'm looking at. But you've taken general chemistry, and we've done this all semester long. You do know what you're looking at. You're looking at an alkene, actually a diene, technically a conjugated diene, and you're looking at hydrochloric acid. You've been looking at hydrochloric acid since Gen Chem 1. So if there's an acid, what is the base? What is the base? Did I have you say it already? The other, which I just described in detail, is the conjugated diene. Must be the base. So I want to show you guys the mechanisms because you know these mechanisms. You did them in Unit 4. We don't necessarily know whether we're going to the kinetic or the thermodynamic product yet, but the first step of the mechanism, sometimes it helps us figure out where to go next. So if we start these mechanisms by redrawing our structures, I'm explicitly showing the HCl bond because the first step of HX addition is acid-base reactions. Don't forget those mechanisms because they're coming back for the final exam. You will have a choice between two mechanisms from the Unit 4 test and a choice between two mechanisms from the upcoming Unit 5 test. So don't forget these mechanisms. Keep practicing them. I'm explicitly showing that HCl bond because the first step of HX addition is acid-base reaction, protonation. In this molecule, does it matter which of my conjugated diene attacks? They're symmetric, so either way, it's going to be the same. So I'll draw it from the top here, but I want you guys to recognize that we could show it from the bottom as well. So I'm showing it from the top on one, from the bottom on the other. We also have looked at the HX addition mechanism a lot. We know what intermediate forms. How can you describe the intermediate? The intermediate is a carbocation. Good. And we know a lot about carbocations now. Can you tell me something that we know about carbocations? More substituted carbocations are more stable. Unless it can be allylic. So what we know about carbocations is that we want to draw the most stable carbocation intermediate. So we can look around and look for the most stable carbocation intermediate. First of all, since this pi bond is attacking, the carbocation will go on one of these two positions. Remember, Markovnikov's rule says H adds to the carbon with more H, which gives you the more substituted carbocation. But now we're actually looking for the more substituted, forget about Markovnikov. Look for the position that gives you the most stable carbocation. I could place a carbocation at this secondary position. Sorry, I'm actually going to redraw that up here because it's not the one we're going to go to. And I could add the hydrogen to the tertiary position. So the change has been made to the tertiary carbon. Nothing has been made to that secondary carbon. Or I could add the hydrogen to the secondary carbon and leave the carbocation on the tertiary carbon. Yes, the carbocation is on the more substituted position. More importantly, this is an allylic carbocation. And this carbocation is isolated from the allylic position by an sp3 carbon, not supported by resonance. So regardless of which mechanism you've shown, we are showing, let me say that a little different. Regardless of which diene you've shown attacking, we want to form the allylic carbocation. And because there's an allylic carbocation, that means that there is now resonance between two different structures. So I'm going to show these resonance forms. Keep in mind that resonance arrows are double-headed, whereas reaction arrows are one-directional. And the arrows needed to show resonance, the pi bond moves towards the carbocation, high electron density to low electron density. Those two structures look pretty different. So if it helps you, map your carbons so that you don't accidentally place the carbocation in the wrong position. I'll start here by numbering the carbocation as position 1, and then the alkene as 2 and 3. Now the alkene is between 1 and 2, and the carbocation is on 3. What I have now are my two allylic resonance forms. And what I can gauge a little bit more easily now is which resonance form will give me the kinetic product and which resonance form will give me the thermodynamic product. Do you remember what pieces of information in these resonance forms help you determine the kinetic product from the thermodynamic product? There are two things that you can look for. Let me ask this. How can I use the substitution of the carbocation to predict whether it will form the kinetic or the thermodynamic product? Good. A more substituted carbocation has a lower energy of activation. That means kinetic product. A less substituted carbocation has a higher energy of activation. That means thermodynamic. Kinetic is the smallest amount of energy needed to form. Thermodynamic needs the most energy. How can I use the alkene in these resonance forms to tell me whether it's the kinetic or thermodynamic? What's different about the alkenes in these? Nothing? They're the same? Even if you forgot the vocabulary, describe it. What's different? Okay? Meaning one alkene has more carbon groups attached, and one alkene actually has more hydrogens attached. So we can say that this is a less substituted alkene, and a more substituted alkene. And what do we know about alkene stability? More substituted alkenes, much like carbocations, much like carbon radicals, more substituted alkenes are more stable. So this has the highest activation energy, but the lowest alkene energy. The highest high and the lowest low. That means that this structure will give me my thermodynamic product. Whereas the lowest activation energy, but the highest alkene energy is kinetic. The least amount of energy needed to form, but not a lot of energetic stability in the product. Highest high, lowest low, thermodynamic. The other is my kinetic. Okay, so far I've shown the mechanism for both products, and they've had the same steps. I actually want this resonance form to get to my kinetic product. Which of these resonance forms exists at any given time? Neither or both would be good answers. That means that if I wanted this resonance form to be drawn to form my kinetic product, but I've already gone ahead to draw this resonance form, it doesn't matter. This resonance form doesn't exist. I can show the formation of either product from either resonance form. All resonance forms can be drawn in an equivalent step. So we had HCl attack, and we formed chloride. Now here's my chloride again, because in my resonance form, the chloride didn't do anything. Here's the chloride. Here's the chloride. For my thermodynamic product, I want the least stable carbocation and the most stable alkene, the highest high and the lowest low. That means that I can show my chloride attacking at this less substituted carbocation. And I get my thermodynamic product. For my kinetic, I could do two things. I could just erase that resonance form that I drew and just go back a step to the other resonance form and just show chloride attacking. But I want to demonstrate for you, you all know how to show that. I want to demonstrate how this resonance form can be used to create this carbocation for the structure. Chloride will attack at position 1. Oh no, that's not where my carbocation is. That's where I want my carbocation to be, but that's actually where the alkene is at the moment. So I show the alkene breaking back to carbons 2 and 3. It's okay to use this resonance form as the drawing of this carbocation because neither of these forms exist. They're both just all right approximations of the structure that I want to show. So if I want my chloride to attack the carbocation here, then I just break the pi bond. And it is attacking the carbocation there. I get a less substituted alkene, but technically I've attacked at a more substituted carbocation. There's another term that we can use to describe kinetic and thermodynamic products. They can be described as 1,2 addition and 1,4 addition. Based on that terminology, which of these would you label as 1,2 and which would you label as 1,4? One 2 addition and 1,4 addition. Yeah? To show 1,4 addition, meaning something has been added to position 1 and something has been added to position 4, then let's number our alkene let's number our conjugated diene like this. Positions 1 and 2 are conjugated with positions 3 and 4. You can see how those numbers in my kinetic product show that I have only added across positions 1 and 2. So 1,2 addition. Hydrogen added to 1, chlorine added to 2. In my thermodynamic product, hydrogen added to 4, chlorine added to 1. I've done 1,4 addition. The name 1,4 addition should leave in your mind what is going on with positions 2 and 3. Nothing is being added across 2 and 3? Correct. Nothing is being added across positions 2 and 3. There's a pi bond left between positions 2 and 3. And it may look like there is no pi bond between 2 and 3. But that is just an illusion. How much harder does this feel compared to just typical HX addition? Same level of difficulty, especially compared to when you first started doing HX addition? Or does it feel like a new level? Yeah? What things do you have to consider here that you didn't have to consider in just standard HX addition? Now you have to consider the stability of the carbocation formed. You had to do that before. There is an added complexity now. That carbocation is allylic and it's in resonance. Either resonance form. Correct. Correct. All right, we've talked a bit about MO theory. I think rather than having you copy this down, I'd like you to just take a look at this graphic for now. These are representations of conjugated dienes molecular orbitals. At the lowest energy, at the lowest energy, we see that the pi orbitals at each atom are in phase with each other, which actually just gives one molecular orbital. That is to say, there is a pi bond not between two atoms, but a pi bond between 4 atoms. So when you look at that thermodynamic product that we had, and it says 1,4 addition, there's a pi bond between 2 and 3. How is there now a pi bond between carbons 2 and 3? There always was a pi bond between 2 and 3. It was between 1, 2, 3, and 4. So that actually isn't new. It's just not how we it's not how we displayed the structure. And then I want you to look at this. This is pi 3 star. It's an anti-bonding orbital. This is the LUMO, lowest unoccupied molecular orbital. And so this kind of helps explain some of the governing chemistry of how the conjugated diene can react. And look at positions 2 and 3. It looks like they have a pi bond. So if the LUMO is involved in any way in the reaction, then you can end up getting that pi bond between 2 and 3. But when you look at the HOMO, the highest occupied molecular orbital, this actually resembles more closely how we draw the conjugated diene. 1 and 2 have a pi bond, 3 and 4 have a pi bond. And so I'll either see electrons leave from between 1 and 2 or from between 3 and 4, because those are the highest energy electrons, and they're isolated into those 2 carbon pairs. What the molecule actually looks like at one level, this is the highest energy electrons, and so the electrons that we would actually see behaving. But it's not an electron pair at 1 and 2 or an electron pair at 3 and 4. It's an electron pair at 1 and 2 and 3 and 4 out of phase with itself. Super odd behavior, but we love to see it. All right, I want to remind us of that worksheet that we have. Oh, I didn't bring it. So if you need it, I'm sorry. Maybe during the break I can run down and grab the extras that I have down in my office. It is on Canvas. Yep. It's on Unit 5, and it's labeled as Organic Synthesis and Nomenclature. We are looking at this. And we took up the first 2 rows. We looked at that kinetic addition and the thermodynamic addition. Do you remember how we distinguished between those 2 reactions? Hot. Thermodynamic had HX over the arrow and hot. And kinetic? Negative 70 degrees C, cold. Very low energy, only enough energy for the molecules to react. All right, with these last 2, I want to show you X2 addition. One of them at negative 70 degrees C, and one of them hot. What temperature is hot, by the way? I mean, compared to negative 70 degrees C, 0 degrees C is hot. So is 50 degrees C, so is 10 degrees C. So that temperature, ambiguous intentionally. Do you think you can predict the products that give us kinetic addition and thermodynamic addition? What factors are going to play here? There is no carbocation anymore. So in terms of that highest high and lowest low, we aren't looking at a less stable carbocation and a more stable carbocation. So the game has changed a little bit. But then we also had those other names. 1,2 addition, 1,4 addition, that really highlighted the substitution of the alkene intermediate. So if I'm going for the least amount of energy compared to give it the most amount of energy, I can still look towards what will give me the most stable product, what will give me the least stable product, what will give me the most substituted alkene, what will give me the less substituted alkene. So I want to draw for you guys for a minute the intermediate before we actually look at the final product. X2 addition, does it have a carbocation? Intermediate. Sorry? Carbocation intermediate with halogenation? Oh, you guys got to build a table, right? You got to know these reactions. No carbocation intermediate. Instead, we have the halonium ring intermediate. Now, if there is very little energy in the system, then this halide that breaks off, it doesn't have a chance to move very far. That's generally how I like to make it make sense. that halide stays very close. We're running this at negative 70 degrees C. So that halide stays close, and it attacks always at the more substituted position. And so we see anti-addition, of course, but specifically 1,2 addition, kinetic 1,2. Would you agree, though, that it also is more stable for the halide to attack at the more substituted position? More substituted carbon has a more positive charge, and so the halide is drawn to that more positive charge. But just like we saw with our HX addition, this halonium ring intermediate is almost conjugated. It doesn't actually have an empty p orbital here, but it has some strange interactions with this alkene. So if you give this enough energy, the halide won't attack at the more substituted position. It will attack at the less substituted conjugate position. That would mean higher energy for it to do that, but the result is a more stable product. Halide attacks at this terminal part of the alkene. That carbon already has too many electrons. So the pi bond breaks from that position and shifts over, goes to a carbon that also has too many electrons, and so the halonium ring breaks open. Pay attention to our positions 1 through 4, and you see that we've drawn a 1,4 addition product. And we've gone from a monosubstituted alkene to a disubstituted alkene. Disubstituted alkenes are more stable, so this gives us a lower energy product. Requires more energy to attack there, gives you a lower energy product. Highest high, lowest low, thermodynamic product. Wicked cool stuff. Wicked for good. Oh, nailed it. Okay, do you guys have questions on these kinetic, thermodynamic products and reactions? Okay. This last reaction is a bit odd in terms of all of the other reactions that we consider this semester. I want to ask you guys about this starting material. Is that the same starting material as this? The one on the left? What is cis instead of trans? Oh, the what? Are you saying the alkenes? Like the alkene is a cis alkene instead of a trans alkene? You know how we can say like trans 2-butene or cis 2-butene? Is that the kind of situation? The alkene is E or Z? Because you're picking up on orientation of some stuff. not quite, but you're right there. You remember the requirement for an alkene to be cis or trans? Both carbons must have two distinct groups. And these dienes, they both have one carbon that is a CH2 carbon. So the alkenes themselves are not cis or trans. They don't meet the qualifications. Would you guys agree that these are both 1,3-butadiene? So then what is it that is different about them? Go from zigzag to zig-zig. That's a change in what? Conformation. Configuration is like going from R to S or trans to cis. Conformation is just rotating around a sigma bond. And that's actually this sigma bond. So we can actually describe these conformations of conjugated dienes as relative to the sigma bond, the alkenes are trans, or relative to the sigma bond, the alkenes are cis. We call this S-trans conformation and S-cis conformation. Conformations of our conjugated dienes. The name of the reaction that we're considering is the Diels-Alder reaction, which tells you exactly nothing about what is required and what is formed. So I like to call this, the more technical name, the 4+2 cycloaddition reaction. And you can kind of see that in the structures now. There's a structure with 4 carbons. There's a structure with 2 carbons. And they are going to form a ring. This will be a cycloaddition reaction. Here's how I want us to number them. Positions 1, 2, 3, and 4 will always be the conjugated diene. How many of you did this in lab today? Yeah, you see it clicking now? Positions 5 and 6 will be something that loves reacting with the diene. And we call that, of course, a dienophile. I'm going to write out these words in a little bit. Actually, I think I'll write it out right now. Diene reacts with dienophile. What size ring are they going to form? A 4, 5, 6, or 7-membered ring? 6. All 6 of those carbons give us this cyclohexane template. 1, 2, 3, 4, 5, 6. So there's a few changes that you can see, correct? Carbon 1 is now bonded to carbon 6, and carbon 4 is now bonded to carbon 5. So there have been bonds created. If you will, 2 new groups have been added to the diene. But there's another feature in the product. Always, always, in these Diels-Alder reactions, there will be a pi bond remaining between positions 2 and 3. Okay, some requirements. S-trans dienes do not have the conformation to react. So these must be S-cis dienes. For something like 1,4-butadiene, that's not hard. Give it a little bit of kinetic energy, a molecule will bump into it in just the right way that it starts spinning around its sigma bond, and it rotates into that S-cis conformation and it can react. But there are some chemicals that are conjugated dienes that will never react. Here is a locked S-trans conjugated diene. You can see that that diene has that zigzag conformation, and because that diene is part of a ring, it will never be able to react through a Diels-Alder reaction, maybe through kinetic and thermodynamic reactions. This locked S-trans. Those of you that were in lab today, you used a very common Diels-Alder starting material, cyclopentadiene. This is what we call a locked S-cis diene. Some other things to know. The dienophile can be an alkene or an alkyne. And the thing to note is, regardless of the functional group, 1 degree of unsaturation is consumed. 1 pi bond is consumed. The alkene only has 1 pi bond. So in the product, that degree of unsaturation is gone. But the alkyne has 2 degrees of unsaturation, 2 pi bonds, which means in the product of a reaction with an alkyne dienophile, you're left with a second pi bond. For instance, that 1,3-butadiene reacts with acetylene. It doesn't leave us with cyclohexene. Instead, it leaves us with 1,4-cyclohexadiene. Only 1 of those degrees of unsaturation is consumed. The last note here is that the dienophile often has these electron withdrawing groups. We call them EWGs. What that does is it helps remove electron density from the pi bonds at carbons 5 and 6. It makes the dienophile more reactive to the cycloaddition. So these electron withdrawing groups are things like nitriles, carbonyls. It's pretty much all you're going to see. Those of you that were in lab today, your dienophile was maleic anhydride. The carbonyls of maleic anhydride increase the reactivity at the dienophile, carbons 5 and 6. It just turns out that those 2 carbonyls are also connected to each other by an oxygen. Creates another ring. All right, one last thing. And this has to do with stereochemistry, so it's very relevant to what we covered a lot in this class. When the alkene acts as the dienophile, the configuration of the alkene impacts the stereochemistry of the product. The alkyne doesn't create stereocenters. The alkyne will leave you with the alkene, and so you're not stuck with chiral carbons, but alkenes give chiral carbons. So here's a good way to recognize this. Cis alkenes give cis chiral carbons, R and R, at positions 5 and 6 on the ring. And trans alkenes give, let me draw this a little bit better. Trans alkenes give trans chiral carbons. There's some really cool video graphics that you can use to kind of understand how these structures are reacting, how they fall onto each other to react. But these are really just the shortcuts, the basics. Now, in general, I don't like to get too complicated when testing you on these questions. So I like to show you how to dissect all of them, how to extrapolate the information quickly and easily. But Diels-Alder reactions can get incredibly complicated. It's fun how complicated they can get. So I'd encourage you to not be shy about looking into Diels-Alder reactions, but just recognize that we're going to take it pretty easy. I want to show you the... Oh, that's terrible. I want to show you one of these reactions. You guys know where to go to see three-dimensional reaction displays? Where do you go, Peter? PubChem? Oh, yeah, PubChem will show you like individual molecules in 3D, but if you want to see a reaction in 3D, I'm sorry, I know you guys are actively working on copying down the board. I apologize. ChemTube 3D. Symmetry at Otterbein also just shows you one molecule. ChemTube 3D will show you these reactions. This is listed under their organic header. Oops, I hate doing that. And they've actually got Diels-Alder in its own category. And they've got a lot to say about Diels-Alder. Again, that's because you can get really into this. Here's the reaction that you guys ran in lab today, or that you guys will run in lab this week. This is maleic anhydride on top, and this is cyclopentadiene on the bottom. And what you can see is that these molecules are not running into each other, but rather, like pancakes, they're falling on top of each other. And that's because the molecular orbitals that are needed... Oh, I wish I could see the molecular orbitals. Are pi-shaped molecular orbitals that need to sit on top of each other. There was that formation of the two new bonds. Carbon 1 is bonding to carbon 6. Carbon 4 is bonding to carbon 5. You can see that these two molecules are just falling right on top of each other. And when they do, they create these two chiral carbons. They also create a new six-membered ring. Should I try and see if I can show you the molecular orbitals? Or do you want to see more reactions? Let's just apply it, shall we? Yeah, I don't know that they have any. Here's a reaction where an alkyne is acting as the dienophile. And you can see that it leaves you with the alkene. That alkene really doesn't have any choice of configuration. Those two groups are always just going to be coming off of the alkene. But in the same way, it still made that six-membered ring. I want to see if you can see that six-membered ring a little bit better from this angle. Here's positions 1 and 4. No, that 6-membered ring is at a bad angle. There's that 6-membered ring that it forms. Okay, so let's look at some reactions. Two, 3-dimethyl, 1,3-butadiene. Reacts with cis 1,2-cyanoethene. 1,2-dicyanoethene. First thing I'm going to encourage you to do is label carbons 1 through 6. You can always label the diene as carbons 1 through 4, the dienophile as carbons 5 and 6. Can we say whether the chiral carbons at 5 and 6 will be both wedged or both dashed, in other words, cis groups, or will they be trans? Will one be wedged and one be dashed? Cis. I've got a cis alkene. That's going to lead to a cis configuration at the chiral centers. When you draw your product, start with a 6-membered ring and a pi bond between 2 and 3. That cyclohexene template is always the answer. And then start to fill in your carbons so that you know where everything else is going to come in. Off of carbons 2 and 3, I should have methyl groups. Off of carbons 5 and 6, my cyano groups are both wedged or both dashed. Can anyone confirm for me that carbons 5 and 6 are actually chiral? No? Not confident? Confident? Cyano, hydrogen, a carbon in the ring that's part of the close to the alkene, a carbon in the ring that's not close to the alkene. 4 different groups. And the molecule as a whole, chiral, achiral, or meso. Meso. Which means I don't need to draw another product. That's it. That's the only product. Okay. No, definitely not. Imagine that, should we just look at it? Imagine that this same group here was trans instead of cis. Okay, this time I'm going to use 1,2-dimethylene cyclohexane. That is a locked cis conjugated diene, S-cis conjugated diene. I've basically got 2 CH2 groups coming off of my cyclohexane. And let's look at, well, I guess let's switch it up a little bit, and let's make these a carboxylic acid group. So we're looking, instead of at a cis alkene, we're looking at a trans alkene. Aiden, do you feel that I could have just as easily written CN, and it would have, you see the comparison between our first group and our second group? I'm going to label positions 1 through 4 and 5 and 6. When I start predicting my product, what should I draw? Cyclohexene. always draw cyclohexene. Cyclohexene will be in the product, always. And then label positions 1 through 6. That double bond is always at positions 2 and 3. Okay, but this time, positions 2 and 3 have an entire ring connected to them on the other side. You agree? Position 2 and 3 here, they're connected, and they also have this whole ring also connected to them. So I need to draw in that other ring. Positions 5 and 6, they came from a transalkene, and so their groups here, one of those carboxylic acids is wedged, one of those carboxylic acids is dashed. Transalkene leads to trans stereochemistry on that ring. Is that meso, Aiden? That means that I've only drawn one enantiomer. So I can either say plus enantiomer, or I can draw in its enantiomer. Are you guys all right with the fact that I abbreviated the carboxylic acid group as CO2H? It can be so much nicer to abbreviate that group. It looks really funky. I always have this weird challenge with having a wedge to a carbonyl, a CO double bond, or a dash to a double bond. It feels weird to have that, so abbreviating the group works really well here. What would these two products form in terms of a ratio? Would they be 50-50, or is there reason to suspect one might form larger than the other? One might form to a larger extent. How would you know? Do you have enough information? No? What's the relationship between the two products? Enantiomers. And when enantiomers form as the result of a reaction, they always form in a specific ratio. What do we call this ratio? Racemic. Some people say that is a racemate, which is such a funny word. That racemic mixture, it actually comes from racemic acid, which is no longer called racemic acid. But racemic acid was that first chiral compound that was discovered by Pasteur to exist as two enantiomers. And then it later got renamed as tartic acid because racemic came to be known, this 50-50 mixture of two enantiomers. All right, this time we're going to do it backwards. I'm going to give you the product, and I want you to give me the two starting materials. Oh, I'm sorry, I did make a mistake on that. Oops. I wanted these to be dashed in the first product and wedged in the second. You want to try and apply the same skills. Can you identify positions 1 through 5? 1 through 6? If you can, That means you can identify where the pi bond is between 2 and 3. You can lock in on that position. Do you see any electron withdrawing groups? Those electron withdrawing groups should be connected to carbons 5 and 6. Now you need to break carbons 1 and 6, break carbons 4 and 5. Predict the 2 starting materials. Start. Start. No. Let's look back at this one. Oops. And actually, we'll look at a few. 2 and 3 have the pi bond. 2 and 3 have the pi bond. Well, I mean, that is true. This structure gave us a bicyclic, where 2 and 3 were in the middle. Yeah. This structure didn't give us a bicyclic at all. Yeah. So I think it's okay for us to get 2 and 3 to be wherever in a bicyclic structure. But what we can look for is that alkene. That alkene will always tell us 2 and 3. And the electron withdrawing groups, those always tell us 5 and 6. Oh, I think you missed this one a little bit. Oh. It's a CO double bond. Okay. So that CO double bond, that's an electron withdrawing group. So that tells me this group should be connected to carbons 5 and 6. Yeah? Good. Okay. Now, break the bond between 1 and 6. Break the bond between 5 and 4. Perfect. Both of them. Great job. Well done. Oh, I see what you're saying. So now tell me why you want this to be a trans alkene.
Oh, it's not trans. Well, it has the...
Oh, think about the relationship of the two groups to each other. Cis. They're cis to each other, then they should be cis to each other.
And you just kind of ignore.
Yeah. Ignore anything else. Exactly. Got your carbons labeled right. Good job. I think you went from having, did you call that 7? Okay.
Because I counted the carbons on this side and there's no.
Oh, I think you added a carbon here. You should only have 4 on this side and then 5 and 6 on this side. If it helps, redraw your product on the left-hand side and then start erasing the bonds that you don't want to have connected, right?
Yeah.
So you could kind of redraw it, exaggerate the bonds that you want to break, and then erase them. Kind of like how we do the ozonolysis, right? Redraw the structure with a long CO double bond, and then erase the CO double bond and put in the oxygens for the new carbonyl sat form. Redraw the starting material as the product, and then erase the bonds that you're trying to form.
So wouldn't the product on this one have
6, I think 11, because of that methyl group. Yeah. Oh, well, that methyl group, then, you already said it. That methyl group is just coming off of carbon 1. Don't call it carbon 1. Just say carbon 1 has a methyl group coming off of it. Good. Great. Perfect. Keep going. Good start, except those are not 1 and 2. Those are 2 and 3. 2 and 3 are always the alkene carbons in the product. Yeah? Mm-hmm. Okay, I thought you had a follow-up on that. What's going on with these guys?
Yeah, we don't want to.
Is that a cis alkene or is it a trans alkene? It actually almost looks like you've got an alkyne.
True.
But without enough pi bonds. Right? So straighten your orientation, make them cis or make them trans. How does the stereochemistry of the product tell you? You're on the right track. But 5 and 6 always need to be bonded to each other. And 5 and 6 always need to have a pi bond or 2. But your 5 and 6 are not connected. Do you agree that they're not connected here, but they are connected here?
Yeah.
So they need to be connected here, and they need to have an extra pi bond. Yeah? You're very close. On the right track, yep. Except none of this exists. 2 and 3 are bonded to each other. 2 and 3 also have H's coming off. They don't have.
Oh, really?
They don't have a ring.
Oh, okay.
Whereas 5 and 6 are connected to the carbonyls, and the carbonyls are connected to each other. So I think
So is this one a ring?
Yeah.
Then? Okay, I gotcha. Thank you.
Yes. Perfect, Elise. Now convince him.
So they, yeah.
Perfect. Nailed it.
I'm gonna redraw some of this video.
All right. We should have 2 groups. 1 through 4 and 5 and 6. We can identify 1 through 4 because 2 and 3 need to have a pi bond. So I could even start by just saying 2 and 3 are the alkene carbons. 5 and 6 should be bonded to some electron withdrawing groups. Those are the ketones here. Now a lot of you took our last example. Look at what we've done. We formed a ring, we formed a ring, we formed a ring, and then in this last example we formed 2 rings. And a lot of you took that last example and you said 2 and 3 were kind of the connecting point, the bridge carbons between the 2 rings. And so then down here you said 2 and 3 will need to be involved in some way in that bridge carbon, but they're not. 2 and 3 are actually bonded to hydrogens. What is the bridge carbons are 5 and 6. So 5 and 6 are connected to these carbonyls and connected to the rest of this ring. 5 and 6 then just need to have an alkene between them. That leaves me with 1, 2, 3, and 4, where 1 is also connected to a methyl group. You actually don't have the information to know whether this methyl group should be trans on the alkene or should be cis on the alkene. So if you gave me Z13-pentadiene, or if you gave me E13-pentadiene, I would give you either of those. You didn't have enough information. But a lot of you just took the bond line as it was, and you ended up with the Z13-pentadiene. Understandable. But technically, either of these could lead to this product. There is a lot more that goes on in here. There's descriptors like kinetic and thermodynamic, but in the context of Diels-Alder, they're often called indo and exo. Those of you that took the lab, you had a little read up on this. Indo isn't necessarily an endothermic process. Exo is not necessarily an exothermic process, but it's more about how they relate to each other. One product is higher in energy, kinetic, which means it's more endothermic than the other. One product is lower in energy, it's exothermic compared to the other. But generally, Diels-Alder reactions are usually exothermic regardless. Okay, what do you think? If I gave you one of those three, do you think that you could pick apart the piece of information that was missing? I also want you to recognize that we draw these reactions a little bit differently. It's not so uncommon to show both starting materials on the left side of the arrow. But would there be anything wrong with saying that I take 1,3-butadiene and then I take this new ketone structure and I put it over the arrow? No, nothing wrong with that. Or I could switch it, right? Remember, we said this early on when we talked about reaction arrows, that that's just a place where chemists like to play around and conserve space. So you can put them next to each other. You could put either one of them over the arrow. A lot of different ways to communicate these reactions. I've forced you to go a little too long on this. Why don't we take a 5-minute break, and we're going to transition into alcohols and alkyl halide substitution reactions and elimination reactions. Let's come back at 6:20. You have time to pull up that problem?
Yeah, no, I was looking at it. So I drew it, and it's that.
Mm-hmm.
Okay, I finally did that and it didn't work. Maybe I just like clicked the wrong one. So that one.
Let's try it.
Last attempt, so I'm like,
Oh.
shoot. You're
Got
kidding. I was so mad.
I wonder, because the combinations are crazy.
Yeah.
It'll give you combinations that don't exist, right?
Yeah.
It'll show you 3 lone pairs and a positive charge that doesn't exist.
Yeah.
So if it's possible you clicked on any of the wrong options.
I probably did that.
Yeah.
I had like my friend that literally passed OChem with an A, and I was like, "Can you figure this out?" And we were.
And you know what the problem is? The answer you had was correct.
So yeah.
And if they said in the directions, oh, they do actually.
They do. And then I was like, okay,
but it's still, it's just like not. They don't always say that.
Yeah.
They're never consistent. That's actually my biggest complaint. I wrote that down to tell them at the end of the semester. They should go through and see if they can make that change.
Yeah.
They have,
like wanting to rip my hair out.
yeah. When you have it right and it just won't give you credit, I know it's not fair. You're welcome. For what? For what major? Oh yeah, no. Right. Really? Oh, I had a biochem major friend in college who did not need to take Calc 3, but wanted to take an extra chemistry class with us, but wasn't allowed because you need Calc 3 for those physical chemistry classes. That's why chemistry needs Calc 3, is for the, in Gen Chem when you learned about orbitals and how they are mathematical functions that define the shape of where an electron might be, that needs 3-dimensional calculus to derive. So you can't do that highest level of chemistry without Calc 3. But Calc 3, it's a breeze. It's the easiest of the calculus series. Calc 2 is the hardest. So if you have a good grasp on Calc 2, like if you can get through Calc 2, Calc 3 will be a breeze. I remember being, I remember being scared when I got to calculus. My brother failed Calc 2 twice, and then he passed Calc 2 with a C the third time, and then he failed Calc 3. And so I was like, whoa, Calc 3 is going to be so hard. I got to Calc 2. It was hard, but I managed to get by. And I got to Calc 3, and it was just like, wow, thank you. It's so easy. It's like literally the same stuff you do in Calc 1 and 2. You just add a different dimension, and it's so easy. It'll be good. Oh, but you're avoiding it? No, you don't have. You have to still take it for your biochem requirements. It's okay. You're in the home stretch. All right, guys. We have been cycling back to nomenclature over and over all semester. And I really do that just to make sure that you guys still feel comfortable with nomenclature and that you're not forgetting it. Something I like to do on final exams, and I need to start putting into unit tests so you get more practice, I like to have questions that don't have chemical structures at all, and they just have names. So it'll say something like, what product forms when 2-pentanol is dehydrated with sulfuric acid? 1-pentene, 2-pentene, E-2-pentene, Z-2-pentene, right? Just have nomenclature and not have any structures, because that is an important skill in this class, is walking out the nomenclature. By the way, the U doesn't teach nomenclature. They just expect you to learn it yourself. They test you on it, but they test you on it. They will test you on nomenclature. They just will not teach it to you because they consider it such an easy thing. I don't know. And it's not hard, right? We've gone through it over and over, and it needs some review, but it's straightforward at least. It's tedious and boring a little bit, sure. So what do we know about alcohols? We've been reviewing this all semester. Compared to alkenes, alkynes, alkyl groups, and halo groups, where do alcohols sit in terms of priority? Good. Alcohols sit as our highest priority group. And they give us a suffix stopper. Again, I've not seen anybody else that calls it this, so I think I made it up. But it just makes sense to me because you still need a suffix. You need something like ane, which becomes ane-ol. You need something like een, which becomes een-ol. Or you need something like ein that becomes ein-ol. Or you can even have een-ein, which becomes een-ein-ol. And the priority rule comes in making sure that the alcohol gets its lowest suffix. Do not pay attention to anything else. Unless it turns out that the alcohol could have the same locant, either way you number it. In which case you just run down the line. So the priority is for the alcohol first, then the alkene, before the alkyne, then any alkyl or halogen groups. If there's a tie at the highest priority, move to the next priority. If there's a tie at the next priority, move to the last priority. If there's a tie at that bottom priority, go alphabetical. So in this first compound, this ring, what carbon should be carbon number 1? Where the alcohol is. And do I need to say that that is carbon number 1? In a ring, how do I decide where to start? Just go to the highest priority group. And so if there's an alcohol, that is position 1. It can be assumed. It wouldn't be wrong to add it in, but it's not necessary. So then relative to that alcohol position, I have a methyl at position 1, a bromine at position 4. It does not matter how I number this. There's only one name here. 4-methyl, 1-bromo, cyclohexanol. No? Natalie? I meant to, yeah, well, yeah. I can understand why you all made that face at me. Yep, it was, gotcha, April Fool's Day. That didn't even, I put the number in the right spot. Yes, you need to alphabetize. Bromo comes before methyl, B before M.
You got the day right, but I think you're about 4.
You knew I was going to put the bromo first because I put 4. Anyways, okay. Which way should I number in this chain? Start on the right. I want my alcohol to have its lowest position. Now here's something that some students hear in that. They say, I'm not going to start at position 1. I'm not going to start at that methyl group. I will make the secondary carbon position 1, and I will just have a methyl substituent coming off of position 1. That gives the alcohol the lowest locant possible. It gives the alcohol position 1. But it does not give you the longest carbon chain. And that's still a priority. We're looking for the longest parent chain possible. So our name here, 5,5-dichloro. Pentane 2-all, or you can call this 5,5-dichloro 2-pentanol. Remember, IUPAC likes it when you put the locant right before the indicator, right before OL. But most people will put it in front of the entire root if they can. And I say if they can because when there's an alkene in there, you can't put it before the whole root. You have to put the alkene somewhere as well. Here's another mistake a lot of students make. They will put 5-dichloro-2-pentanol. What's wrong with that? Well, what if it was 4,5-dichloro? What if it was 1,5-dichloro? How do I know you didn't just make a mistake and forget one of your locants? Be redundant. It doesn't matter if they're on the same carbon. If there are 2 substituents, there should be 2 locants listed. How about my next one? Which carbon should I start at and which position or which direction do I move? Where should I start? Let's be descriptive. This one? And then move which way? Counterclockwise? So I would have a 1,5-diol. Okay, so a 1,2-diol. Prioritize lowest locants for both of my alcohols. And then that gives me a alkene at position 4. But I could also have a 1,2 diol going the other way. So I actually have a tie in this case. I can have 1, 2, 3, 4, 5, where my alcohols are at 1 and 2, and my alkene starts at position 4. Or I can have 1, 2, 3, 4, 5, where my alkene starts at position 3, and my diols stay the same. I have two options that don't impact the locant of my alcohol. I move on in my priority list. Now I'm prioritizing the lowest locant for my alkene. Should I number in blue or should I number in green? Number in green. Keep in mind that does maximize the total locant set, because now I have a methyl group at 5 when I could have had an alkene and a methyl group at 4. But that's not the point. The point is prioritize in order. All right, so here I get 4-methyl. I think I said something wrong earlier. I think I said I have a methyl group at 5 now. Sorry, I misspoke. 4-methyl cyclopent what? Good. 3-ene. And you know how typically we remove that E at the end of the suffix so that we can stopper it? Well, this suffix stopper needs a multiplier. This is going to get diol. And that suffix stopper, because it starts with a consonant, not a vowel, it means the E gets added back in. So we get ene diol or ene triol. I think it's about the way that it rolls off the tongue is the rule that they came up with. So we say pent 3-ene 1,2 diol. Correct? I can't say 1,2 all. I need to say that there are 2 alcohols, so it's 1,2 all. I could have also called this 4-methyl 3-cyclopentene 1,2 diol. I can take the suffix and put it in front of the root, but this time I can't take the suffix stopper in front of the root because I have an important locant describing my suffix and I have important locants describing my suffix stopper. So my suffix stopper always needs its locant back here in this case. You guys see why IUPAC says just put the locant in front of the indicator. Don't put it in front of the root because then it gets messy when you have multiple things past the root that need different locants. All right, can we draw these? 1, 2, 3, 4, 5, 6, hexane, hexol. That is not a ring. That is an alcohol at every carbon in the 6-membered chain. This is actually a compound called sorbitol. You guys know sorbitol? Fake sugar. Yep. So hexane, 6-membered ring. Position 1 has an alcohol. Position 2 has an alcohol. Position 3, 4, 5, 6. That's a fun structure, right? And a funny sounding name, too. Hexane, hexol. All right, now here's a good one in my opinion. 4-phenyl, bute 3-ine, 2-all. Where do you want to start with this? When you're drawing it, I like to start with the parent chain. But there's an alkyne in here, so I don't want none of this zigzag business. I'm going to start by drawing an alkyne and drawing things off of that alkyne, and then finish the parent chain from there. So I know my parent chain is 4 carbons long, bute, and I know I've got this alkyne at position 3. Doesn't really matter which way I number position 3. But if the alkyne is at position 3 on a 4-membered chain, then the alkyne spans 3 and 4. So the alkyne is the end of my chain. So I'll have a bond that goes from position 3 to 2 to 1. Boy, you know, the way that looks sure looks a lot like 1-butyne. Why is it but3-ine? It's because my alcohol takes priority on position 2. 1, 2, 3, 4. And off of position 4, I have what substituent? pH, acidity. No. Phenyl, which is what group? We could put pH. I'd give you points for it. If you put pH coming off of it, but phenyl is any ring. Just pick a ring. It doesn't matter. A benzene ring, the aromatic ring. There you go. Tell me, I count 6 carbons. Do you want me to have the alcohols pointing a little differently? 1, 2, 3, 4, 5, 6. I mean, I could have this alcohol come down. That's just a different conformation. Or I could have this alcohol come down, but that's also just a different conformation. Okay. You know what? I felt the same way when I was showing you those kinetic thermodynamic halogenation products. It looked like I was adding a lot of extra carbons, but it was just the way the bonds to the bromines went. Yeah, same molecule, just a different conformation. All right, you guys feel good on your nomenclature? Don't forget to practice it, because it doesn't go away. And I love to ask those questions. Which of these is the product formed in the reaction? And I'll just give names, and you have to know what the structure looks like and what its name is. You know, one thing that I like to do in my OChem 2 course, we go through a lot of functional groups. So I like to take things like aldehydes, and we'll go through all the reactions that form aldehydes. And then we'll go through all the reactions with aldehydes as a starting material. We actually do that with alcohols too. We have a whole chapter where we review all of the different ways to make alcohols. How many ways have we seen how to make alcohols? Let's think about from the alkenes. What alkene addition reactions make alcohols? Hydroboration oxidation. Acid catalyzed hydration, the classic. Diol addition. Oxymercuration reduction. And halohydrin addition. X2 in water gives a vicinal halohydrin, a halo alcohol. So we've seen a lot of different ways to make alcohols. Now we're going to look at ways that we can react with alcohols. First, I actually want to look at these previously seen reactions. Previously, we saw that we can use things like thionyl chloride to substitute an alcohol for a chlorine, and we have some control over the stereochemistry. We can actually invert the stereocenter using thionyl chloride. And we can take an alcohol and we can react it with phosphorus tribromide. And in the same way, we can substitute for a bromine and invert the stereochemistry. So we have already seen substitution reactions with alcohols. I want to show you a few more substitution reactions. Let's start with this R2-butanol. And I want to subject it to two different conditions. I apologize for not having a worksheet ready for you guys. But you've had some practice with the worksheets, so now you kind of know how you can organize these. First, let's take this alcohol and let's subject it to HBr. This will substitute for bromine, but it gives me a racemic mixture. What that tells me is that this reaction has a carbocation intermediate. When a substitution reaction has a carbocation intermediate, we call it an SN1 substitution. We're going to talk more about that on Wednesday because I'm running out of time tonight, sadly. Unless you guys want to stay until like 10. Wow. Okay. Just kidding. I'm hungry. No, I don't have what? I don't have any. Yeah, go start it. HCl gives us the same thing, but we substitute for chlorine. This gives us a mixture of stereochemistries. Now you guys can kind of see that there's a usefulness to thionyl chloride and phosphorus tribromide. If you need to control the stereochemistry, then these reactions are useful. If you don't care about the stereochemistry, if the chirality is irrelevant, these are really easy. These reagents are cheap. They're easy to get your hands on, and they're less toxic than these reagents. A lot easier to work up. We're going to talk more about SN1 on Wednesday, but what I have evidence for of the SN1 is that they had a carbocation intermediate. Oops. And how do I know they had a carbocation intermediate? The same way that we saw other reactions that had carbocation intermediates gave us those mixture of chiralities. You have a flat achiral carbocation. The new carbon or the new group can attack from either face, giving you R or S configurations on your chiral carbons. The S and the N, they stand for nucleophilic substitution. The 1 is for first order. And again, we'll talk more about why it's first order. Okay, so we can substitute. There's another reaction with alcohols that is similar to substitution, but I like to call it transformation. By the way, if you wanted to head these, this would be substitution of alcohols. I like to call this transformation. The reason I call it transformation is because I don't actually break the CO bond. I'm not substituting on the carbon. I'll be transforming that oxygen from an OH group into an O something else group. We react it with a reagent called tosyl chloride. Now, here's why I like to abbreviate tosyl chloride. It has a very long structure that doesn't make it easy to draw out. And in the product as well, it has a very long structure that is just tedious to draw, tedious to look at. So I like to abbreviate that as TS. That's where some of you the other day when we did that mechanism thing on the backboard, why are we dealing with tennessium or whatever it is? That is a chemical symbol on the periodic table, but it abbreviates this toluene sulfonyl group. Toluene sulfonyl chloride, which is abbreviated as tosyl chloride. So I want you to notice that the OH substitutes only the hydrogen for this TS group. What's a byproduct of this reaction? Not quite. HCl, taking into account the chloride on tosyl chloride. What I have done is transformed the alcohol. That's why I like to call it that. I haven't substituted the alcohol. Notice how the chirality at that carbon stays the same. That's because the CO bond doesn't break. It's just the OH bond that's being transformed. And there are more than just tosyl chloride. There's also mesyl chloride and trifle chloride. They're all called they're all called sulfonates. This like sulfuric acid type motif is a sulfonate, and they behave more like halogens than alcohols do. So we often refer to this group, this OTS, as being a pseudo-halogen or a pseudo-halide. It's not a halide, but it behaves like halogens. And on Wednesday's class, we're going to talk about reactions that halogens go through. Substitution and elimination reactions. All right, last one. For our alcohols, we can substitute alcohols, we can transform alcohols, and we can eliminate alcohols. Typically, you will see this written as one of two ways. An alcohol with sulfuric acid, or an alcohol with H+, catalytic. This is acid catalyzed dehydration. And it is the exact reverse reaction of acid catalyzed hydration. They are equilibrium reactions. Acid catalyzed hydration has a reverse reaction, acid catalyzed dehydration. There are 3 products that can form here. And we're going to talk about all 3 and highlight the one major product that most people list. The first product that can form is 1-butene. This is referred to as the anti-Zaitsev product. Do you guys remember Zaitsev's name? All the way back from Unit 4, Section 6, We had just started talking about organic reactions, and we said that there's regioterms. We've talked a lot about Markovnikov, shit on him a lot. Zaitsev, never did a thing wrong in his life. Zaitsev says the most stable alkene is the alkene that will form. And this is not the most stable alkene that can form. So we call it the anti-Zaitsev product because it's the less stable one. As it turns out, it does form. This forms less than 1%. I don't actually know. I don't have good numbers, but we're going to say a very small amount. There's another product that can form. It's more substituted, but it's still not the most stable. And that's cis-2-butene. This also forms to a small amount. You might call these, I don't know why I put small, that's not normal. What most people will label this as is minor. That's to say it's not the major product. It's a minor product. It forms to a small amount. The major product of this elimination is the most stable alkene that can form from this reaction, and that is trans-2-butene. This we label as the major product. There was a cool reaction that we ran when I was an OChem lab TA at CU Boulder, where we did dehydration, and there were 3 possible alkene products like this. The less substituted one formed less than 1%. The middle substitution, but wasn't the most stable, formed around 5%. And then the other 95% of the product was the most stable Zaitsev alkene. So this is, we call this major, but this is also labeled as the Zaitsev alkene, the most stable product possible. So, question, if I wanted to run elimination on an alcohol, could I use any acid? For instance, could I chuck in hydrochloric acid and try to eliminate the alcohol? Why not? What will grab the hydrogen? Hydrochloric acid? What happens if an alcohol reacts with hydrochloric acid? It just substitutes. This is what we call a nucleophilic acid. It has a nucleophile inside of it. Sulfuric acid we call a non-nucleophilic acid. The conjugate base of sulfuric acid will not act as a nucleophile. What I love to see, I'm just kidding. What I see a lot though is that people will take H2SO4 and they will substitute the alcohol for an SO4 group. They will substitute with sulfuric acid. That's not its role. Its role is selectively eliminate, form an alkene. If you want to substitute, we have acids that do that. So those acids have to be avoided for elimination purposes. All right, on Wednesday, SN1, SN2, E1, and E2 on alkyl halides and pseudo halides. We're going to learn a few more mechanisms, and we're going to build a table that helps us predict what type of reaction happens in different types of conditions for our alkyl halides. And we're done for the semester. All right? Thank you guys for your time. Have a good night. See you Wednesday.